So 4.5 section, applied maximum and minimum problems. Uh, these problems are also called optimization. Whenever we have a statement problem where we need to find the maxima or minima of some subjective function, we call it optimization. Uh, so we will study two types of optimization problems here. The problems of finding maximum or minimum over a finite closed interval, and the problems of finding maxima minima over infinite interval or the intervals that are not closed. So if you review in section 4.4, so in 4.5 is applied maximum and minimum problems. So this is also called optimization. So we optimize functions from the real problems, not just of fx is given and doing. So if you recall in 4.4, in section 4.4, we studied two types of maxima minima. One where the closed interval was given. If my interval is from a to b and your function starts from here like that and stops at b. So the highest value of the function over this whole interval is the absolute maximum value. And lowest value, for example, I can come down here and stop maybe here. Now you see the minimum value of this function is this, b. So this is called absolute minimum. In section 4.2, we studied relative minimum. Relative minimums can be more than 1, but absolute maximum minimum is only 1. So this is a critical point where we are getting maxima, and end point we are getting minima. So anything can happen either at the end point or the uh, critical point. So your absolute maximum or minimum may occur at an end point or at a critical point. So what we do, we find critical points of the function and we calculate the function values. For example, the function value at first endpoint, the function value at a is here, the other critical point is this one, so this is the second value, the third value is this one, and this is the last endpoint. So see, I got four values here. Why? 1 2 3 4. So this is the largest one, so we just pick the largest, gives you the absolute maximum, and this is the smallest one among the values of the function, which gives you the minimum. So finding maximum minima over a closed interval is very easy. Absolute maximum minimum. So the first type of questions here is when you have to find maxima minima over a closed interval. Here, see, over a closed interval. So we will do that. Then we will go on to infinite or not closed intervals. So let's see if we start with a simple example. Let me snip it. I can snip this example. Let's say this is the example. Let me write the page number. The page number is 275. So example on page 275. So see here, a garden. Now applied maximum minimum problems are, we have to find maximum minima, but a certain scenario will be given from the real problems, like real world problems. So we have to apply the concept of finding maximum minima over these problems. Excuse me. That's why they call it applied problems. So see, if I read this, a garden is to be laid out in a rectangular area and protected by a chicken wire fence. So see here, uh, you have to make a rectangular garden, a garden that has a rectangular shape, right? And you have a wire, chicken wire. That is a, you might have seen, it's a steel wire that has some um, so they call it chicken wire fence. Basically, it's any wire you need to fence any area, right? It can be any rope or something like that. So, what is the largest possible area? See now, largest, it means I need to find the maximum area, right? Of the garden if only 100 running feet of wire is available. So now this is the condition that if you just give me any amount of wire, I can make a garden as big as possible, no problem. But now the problem is I have a limited wire. Okay, so for example, if you make 20 feet here, uh, 30 feet here, then this 20 will be here as well and this 30 will be here as well. It's a rectangle, right? So opposite sides are equal. So 30 plus 30, 60 plus 20 plus 20, 40. So total is 100. So this will give me one of the options to make a garden. But here your area will be 30 times 20. You multiply length and width. So it will be 600. On the other hand, let's say if I make it something like that. I keep 10 here, 20 and 40, 40 here. So again, the sum is 100. But this time the area will be 400, 40 into 10. This will be 400. So see, this is smaller than 600. So I don't want this one. I want this one. Right? But maybe there are other options that give me better areas. Maybe more than 600. So by just trying, I may not get exact answer. So it's better to use mathematics that we have studied. So what I can say that, we can say that let x be the length, right? Y be the width of the rectangle. So don't guess. Here what we were doing, we were guessing. We were just making guesses. So these guesses may not be good enough, right? So let's see. I do more mathematical thing. So first of all, I can say that let x be the length of rectangle or the garden. Running feet, you see here, a fence is given in feet, so x and y will be in feet, right? So length of garden, right, in feet, and let y be the width of garden, again in feet. And then next thing is the area, right? So I will also call and a be the area of the garden. Now area will be in feet square. Anything which is area, it is square of the unit, feet square, because we multiply feet with feet, x into y, so it will become feet square. Now then what is my, how I can relate these variables? We know that area is a product of the length and the width. We multiply length by width, x, y. But you see here I am having two variables. I have to maximize. I need to find this area as large as possible. But in 4.4, we saw that I had the function of only one variable. These are the functions of one variable only, f of x. This function is f of x, not x, y. I don't have two variables. So this is a problem, right? So when we have more than one variable, look for a condition. A condition will be given. What is the condition here? They said only 100 feet of wire is available. The last sentence, only 100 feet of wire. It means if I add x plus y plus x plus y, it should be 100. If I add all the sides, it should be 100. So basically, parameter. The parameter of the rectangle, that is called a perimeter, the outside length of the rectangle. is a parameter of garden is 2x plus 2y. Two sides of x and two sides of y. So x plus x, y plus y. And that is equal to 100, which is given. Available wire. Right? This 100 feet is the chicken wire available. They call it a chicken wire. It's just a steel wire that has some thing on it. So it's like wire where we have they make something here so that people don't come. You know, if they touch the wire, they may hurt themselves, right? So something like that. Anyway, so now from here you see I can write y is equal to 2y is equal to 100 minus 2x, right? I can send x over there and then divide by 2. So I will get y is equal to 50 minus x. So see, I got a relationship between y and x. I will put this in a now. So therefore, my a will become, therefore we have a is equal to, a was x into y, but now my y is 50 minus x. So see this y, I replace that y here, this y. Agree? We can replace this y 50 minus x in my area. So area will become x into y. Y is 50 minus x. Right? So I got this as a function. Now you see this function is one variable function. Now we have just one variable x. So now we are happy, right? Because one variable I can handle. Two variable was the problem. So whenever they give you two variables, they will give you some condition that will change it to one variable. What? This x, this one? Yeah. We just replace the value of y in xy. You see, what was my area? My area was x into y, right? So I replace this y here. So I got x into y is 50 minus x. So this will become, now I can multiply x inside. So this will become 50x minus x squared. So this is my area, and now I will find the largest area possible. But first let's see if are there any bounds on x. Now you see my rectangle is x and y. So x can be as small as 0. X cannot be negative, right? Because it's the length. Lengths are usually positive, right? So it can be greater than or equal to 0. And if x is less, but it has to be less than 50, not less than 100. Because you see, if I take 50 here, if I take x 50 on one side, right, then I will need 50 to come back, right, and y will become 0. The length will be 0. So 50, 50 and 0, 0, right? If I take x to be 50, my y will become 0. If I take y to be 50, my x will become 0. So at the most, I can take 50. So my x is between 0 and 50 because of the available wire. So see, it's a closed interval. So I can make it a closed interval. Closed interval. Sometimes you can say that 50 and 0 are not physical. Right? Does not make sense. Why? Because if I take 0, x0, the area is 0. So it means you are not making any rectangle. You are just making a length 50 and just coming back. No width, no rectangle. It's just a straight line. Right? So that does not make any sense. And similarly, if I take 50, 50 also does not make sense, because if I take x50, x50, then y will become 0. If x0, then y will become 50. So they just give me straight lines, not the areas. So you can make it an open interval as well. But open interval is little difficult to handle for maxima minima. Right? So if we have an option of making it a closed interval, we can make it. Now it will be very easy. Now what is the solution? Now this is my question from 4.4 now. 4.4 says that maximize area a of x. A is a function of x now. So this is my question. Maximize a over a closed interval 0 to 50. This is my question, and this is a question from 4.4. A function of one variable over a closed interval. What we do, first step is we find critical points. Step 1, critical points. Find critical points. So critical points are where f prime is 0. Find critical points. So for critical points, I need a prime of x. A prime will become 50 into 1 minus x square is 2x, right? The derivative of 50 into x is 1 and x square is 2x. So this becomes 50 minus 2x. Now for critical points, we set a prime x equal to 0. So if I set this equal to 0, it means 50 minus 2x equal to 0, and this will give me x is equal to 25. 50 by 2. Agree? So this is the only critical point, and that critical point is in this interval. So we are okay, right? You see, this point is in the interval 0 to 50. So we are fine. My interval was from 0 to 50, and my 25 is here. So we are okay. It's in the interval. Now the second step, step 2, is evaluate your function, evaluate your ax at critical points and at endpoints. At critical point is x25, and at endpoints are 0 and 50. Endpoints are 0 and 50. X is equal to 0, x is equal to 50. So these are the 3 points where I have to calculate my function. You see here what I did, I recall 4.4, that whatever are my endpoints and critical points. Here there are 3 critical points and 2 endpoints. So we calculated critical points. See the value at critical point, the value at critical point, and the value at endpoints as well. So then I will just look at the largest and smallest value. That's it. So I have only 3 points here, 2 endpoints, 1 critical points. So I will evaluate a at 0, which is 50 into 0 minus 0 square. So that is 0. Then I will calculate a at 25. So that is 50 into 25 minus 25 square. So that is, and then a at 50, which is 50 into 50 minus 50 square. That is also 0. You see, 50 square minus 50 square is 0, but the middle one is 50 into 25 minus 50 square. (25 square), sorry, not 50 square. It was negative, so I was saying why it is negative. 625. So this answer is 625. Now what is the large? We want maximize, right? We are finding the maximum only, not the minimum. We are not interested in the minimum area. Our question is find the largest area. Find the area largest possible. So I am maximizing my a of x. Here we are maximizing. So I will just pick the largest value here. So this is the largest value among these 3. This is the largest, right? So if this is the largest, this means that my area A is maximum or I can say that the maximum or the largest value, the maximum value of A is 625. This is my maximum area, right? And that occurs when x is, if you want to find the dimensions as well, you can write that occurs when x is 25, right? When x is 25, it gives me 625. So this should be my dimension. So what will be y? Y was 50 minus x. See, where is y? Here. Y was 50 minus x. So if I put x 25, y will also be 25. So it means 25 will give me the maximum area, and the maximum area is 625. So this is my maximum area, and that occur at these dimensions. So see what we were guessing at the beginning, right? 20, 30, 40, 10, even 24, 26 will not give me the maximum area. You can try that. So let's see, let's try. If I take x 26 6 here and 24. So this will give me 100 or not? Yes. 100, right? So what will be the area? Area will be 26 into 24. You can find that. It will be 624, I guess. So see, it's less than 625. If you try another one, let's say this the problem is finished. I'm just trying different scenarios. Try let's say 25.1 and 24.9. This also gives you 100, right? 50 plus 50. So let's see, 25.1 multiplied by 24.9. It is 624.99. So your area is 624.99. See, still less than 625. So you can try any other numbers other than 25, 25. You will not get as large as 625. So mathematics will guarantee that this is the maximum area. Okay. So now they wrote it. See, after this example, they wrote this um, as a procedure. You see, these are the procedure that we followed. You see, exactly these 5 steps we followed in the last example. What is the first step? Draw an appropriate figure. That's what we did, right? We made a rectangle and then label the quantities relevant to the problem. We labeled x, y, and area. These 3 quantities were there. And then he said, find the formula for the quantity to be maximized. So, if you want, I can copy this and paste it there on your notes, and I will upload that on Moodle. So it's a good idea to just copy it here. Okay. So see here, if I so this is given on page 276. So this is given page 276, right? So on 276 this procedure is given. So see, first thing is he said draw the appropriate figure, label the quantities. This is what we did. You see in previous example, we draw the figure, we said x and y are the length and width and a be the area. Agree? That's what we did. And then he said find the formula for the quantity to be maximized or minimized. So we wrote in the second step, we wrote a is equal to x into y. Area equal to x and y. Then he said use the conditions stated in the problem to eliminate variables. So and express the function as one variable. That's what we did. So in the third step, we wrote 2x plus 2y is equal to 100, and it gives me y is equal to 50 minus x, and that changes my a to one variable, 50x minus x square. Right? This is what we did. Change to one variable. Then he said find the interval of possible values. So see, we found the interval of possible values from 0 to 50. And then if applicable, use the techniques from section 4.4 to find the maxima. So we did that at the end, finding maxima, minima. Right? So exactly we follow these 5 steps in the previous example. Right? So now this is a procedure we will do this every time. For above example, we did that. So this is what we did for above example, right? So let's try another problem with the same procedure. So he said an open box is to be made this is a snipping tool. If you want to cut anything from your screen, right? So this is a tool to use. You can go to the search box, write SNIP. So see, this is snipping tool. And click on new here, and now select any area on your screen. It will just copy that for you. See, and you can paste it anywhere. So see, I just paste it, Control V, right? It came here, right? Control copy, Control C and Control V, right? What is X? S. I wrote S here. Yeah, S N. S N for snipping tool. S N, right? So this is the snipping tool. So once you get this snipping tool, you can copy anything from the screen and paste it anywhere. So it's a very good idea. So see now, if I do this example, this is on the same page, example on the same page, and see now here. So let's read the question. An open box is to be made by cutting out squares from each corner. Let's say you have a page and you cut out a corner, same corner size, right? Let's say this is a sheet and you cut a corner from here, a corner from here, same, and bend it, right? It will give you a height, you see? So they are bending it. We cut the corners, same square corners, and now bend this along this line, bend it, right? So you will get a box because you bend it, so you got a height. And because they are square, when you bend them, they will exactly meet, right? So let's say these are the squares, so when you bend it, they will exactly meet here, right? You can put some glue, it will become a box, right? Now he said, how we can cut this X so that we get the maximum volume inside, right? The volume inside the box should be maximum. Now it's not the area. The plain sheet has area, but when you have three-dimensional thing, length into width into height, like this room, you can put something in it, right? You can fill it with something, so that gives you the volume. So now they ask me to how much equal size this by cutting the equal size. So question is, what side should the squares be? Means these squares that we are cutting, right? What should be the size of these squares to obtain the box with the largest volume? Okay. So now the size of the sheet was given to me. The complete sheet was 16 inch by 30 inch. So the complete sheet was 60. So this was 30 inch, this was 16. So because we are cutting squares from the side, squares, so squares have the same side. So we don't have to call it X and Y. We can just call it, this is X and X. The size of the square, the side of the square is X by X, right? So just X be the side of the square. And after cutting it, let's say a square is gone from here, a square is gone from here. And when I bend it from both sides, the length of the box will become 30 minus 2x, right? Because 1x gone from this side, 1x is gone from this side. We bend it. So the new length of the box is 30 minus 2x. And similarly, the width will be 16 minus 2x. Because total was 16. You see, from here to here, it was 16. But when I cut x from here and cut x from here, this remaining portion will be 16 minus 2x. When we cut x from here, right? So the remaining length will be 30 minus 2x. So it means if I let x be the side of each square that is cut from the corners, from each corner, right? So if it is then the length, then the dimensions, we can just say that, length, width and height, they are called dimensions of the box. Okay. Then the dimensions of the box are what? The length is 30 minus 2x. This will become the length, right? And the width will be 16 minus 2x, this will be your width, right? 16 minus 2x. And the height, the box will have height as well. Height will be x, because you see, you cut the x side here and bend it. So exactly the same x goes up. So the height is x. So this is the height of the box here. This is the height of the box. So these are the dimensions. Then the volume V of the box is then the volume V of the box is length into width into height. Length into width give you the area of the sheet. But if we have height, multiply area by the height to get the volume. Okay. So x, y, z. So see, now I do not get two variables here. You see, in this expression, I have only one variable x. And this is the reason they did not give you any other condition in the question. You don't need any condition. So there is no step 4. Sorry, step 3. Step 3 is not there. He said find the conditions which changes your equation, eliminate the variables. I don't need to eliminate the variables here. So no step 3 here. So I did step 1, make the figure, label the variables. Step 2, write the functions that we need to maximize. Step 3, eliminate variables. There is no step 3 here. Step 4, write the interval for x, right? X is again the height. So x has to be greater than or equal to 0, right? X is the size of the square, has to be positive. And what can be the maximum size? Look at here. If I am cutting the square, I can cut maybe half of the side, right? I cannot cut the full side. If I have a sheet, I can at the most cut the half of the sheet and bend it. Not more than that, right? And I cannot cut the half of 30, half of 16, which is the smaller one. See, this is the sheet, we are cutting the sides. If this is the smaller portion, this is the larger portion, I can only go this far, the half of this side. I can cut 8 by 8 here and then, right? From both sides. If I take 15, the other one, half of the 15 will not take this one. It will not allow me to bend from here, right? It will only allow me to bend from here. So I take the smallest length, not 30, I will take the 16 and half of it, because I am bending it from both sides. So 8 and 8 can be the maximum. Okay, so your x can be as large as 8. Okay, this 8 comes from 60 by 2, smaller of the sides, smaller side. Don't take the length, it's the width. We take the width and divide it by 2. Why we divide it by 2? Because you see here, I'm cutting the square. So look at here. If I cut this is the half of the width. If I cut the square of this size, this is gone, right? So if this was 16, it has to be 8 at the maximum. So this is again a closed interval. So again we got a closed interval, so it's easy to deal with. Okay, so good. I can multiply this inside. We multiply this with here and then x inside. So I think I can write directly from here. It is 480 minus 92, 480x minus 92x square, 480x minus 92x square plus 4x cube. Okay, so if you multiply all these things, you get this one. Now, what is my question now? I was looking for the largest volume. So it means I have to maximize my volume, which is a function of x, over a closed interval. which is my interval, closed interval. Over the interval, zero to 8. This is my question. So see here, the same interval, 0 to 8. So this is my maximization problem now. Now let's do two steps, right? I know that the step 1 is find the derivative of x. Derivative of x will become 480 minus 92 into 2x plus 4 into 3x square. 480 into 1, right? 480 into 1. So that becomes 480 minus 184x plus 12x square. So if you set this equal to 0, set v prime x equal to 0, you will get 480, or we can make here these are the factors of this expression. So if I put it equal to 0, my x minus 12 will be 0, or 3x minus 10 will be 0, right? Either this will be 0 or this will be 0. So from here x will be 12, and from here x will be 10 by 3. Minus 10 will go there, become 10, and we divide by. This we will ignore, right? Why we will reject this? Because it's not in the interval 0 to 8. It's 12. So I will reject this. Reject this one and accept this one. This is the only critical point in my interval. Why I rejected this? This is the only critical point in 0 to 8. So I will accept this. This is 3.33, 10 by 3. 12 is out of the interval, so I will reject that. I don't need it. Okay. So now a final step was evaluate my function at, evaluate our Vx at critical point and at end point. At x is equal to 10 by 3, critical point, and at end points. End points are 0 and 8. Right? So this is what I have to do. So what is this? I can write that. We are evaluating at critical point, and these are end points of the interval. So let's do that. V at 0, V is 480, x minus 92, x square plus 4, x cube. So that is 0. Now V at 10 by 3. So that is 480 into 10 by 3 minus 92 into 10 by 3 square plus 4 into 10 by 3 cube. And then V at 8. 8 will also give you 0. Reason is when you take the square of size 8, which is exactly half of my sheet, and bend it, it will give you another sheet which is half. No volume inside, right? So volume has to be 0 at 8. But you can calculate, you will get 0. Okay. Whatever we are doing is sophisticated. So it will match with the real meaning. Sorry, not 10 by 3, it's 8, sorry. Right? So if you calculate, it has to give you 0. So let me check what is this. So it is at 10 by 3, it is 726 almost. You can calculate from the calculator. So it is almost 726. So this is the largest. Then we compare which one is the largest. This is the largest, right? So hence we can say that because this is the largest, so we can say that my volume is maximum. Hence the volume V is maximum, is largest. You can see anything. The largest if when x is 10 by 3. This is the value of x, right? When x is 10 by 3, I am getting the maximum volume. This is the volume. This is the largest volume. Okay. So largest volume is 726, but that occurs at 10 by 3. So he asked me what should be the size. You see here, he did not ask me the largest volume. He said what size should the square be. It means they ask me what is x. That gives me the largest volume. So I told you x has to be 10 by 3 to get the largest volume. Okay. And if you want, you can write the largest volume as well. You can say that the largest volume will be 726 inches cube, right? So see, interesting problems, but have to be. So these 4 examples, I will suggest you to see this example 3 and example 4. They are also are the examples with closed intervals. Let me go to open interval 277. Here is the open interval. Let me write here first. See example 3. See example 3 on page 277. Okay, so I'm leaving it for you because it is also an example of closed interval, not the open interval. So we can go to infinite or open interval. So now the examples with infinite or open interval. Problems involving intervals that are not finite or closed. Okay, so this is the issue. If interval is not closed, I do not have endpoints. This is the problem. So if there are no endpoints, I cannot compare. I cannot do this thing basically, what we did at the end. I cannot compare the values at the end with the critical point. Okay, so we may have a problem for with that, but let me copy this. Going to the snipping tool again. So problems involving, or let me just copy the example. Okay, so this is on page 279. 279. Problems involving intervals that are not both finite and closed. Page 279. Okay. Problem with infinite interval. Now it's not a closed interval. Previous example were with the closed intervals. Okay. A closed cylindrical can is to hold 1 liter of liquid. You see, we usually have drinking juices and Pepsi type things, right? Usually they are in cans, right? So can has a circular shape at the top and bottom, right? A circular shape at the top and bottom, and then it has a height. He said, how should we choose the height and radius? So we can say that let h be the height, right? And r be the radius, right? To minimize the amount of material needed to manufacture the can. Okay, now he said, I want to make a can which hold 1 liter of juice or whatever liquid in it. But I want, what I can do, I can make different. I can take height longer and maybe a radius small, right? Or I can take a radius large and height smaller. Both can hold 1 liter, no problem, right? If I am making it thinner, I have to make it long because the volume inside should be 1 liter. If I am making it short, not tall, then I have to make it wide, right? You see, usually 1 liter cans, exactly perfect can shapes. If you go and buy, this butter, right? Usually the butter cans have exactly this shape, and usually they are 1 liter, right? Marai and others, right? So now here height is more, radius is small. Here height is small, radius is large. So I don't know what will happen. But everyone should hold 1 liter. 1 liter inside, right? 1 liter inside. 1 liter inside. So let h be the height and r be the radius, right, of the circle. Height of cylinder, height of can, and this can be in centimeter. Height of can in centimeter, right? And let S be the surface area. Why we are uh, calling this a variable, the surface area? Surface area will be in centimeter square. He said the material needed, minimize the material needed. Where is the material? Material is inside or outside? Inside is the volume. Material for the can, right? So outside is the material of the can. Whenever you have a 3D shape, right, this outside is all the material. This is called the surface area. When you have a plane figure just has an area. But when we have a 3D object, an outside layer area is basically called the surface area. We have to minimize the surface area. If the surface area is smaller, I will get low cost, right? I have to spend low money on that. If the area is large, then my cost will be more. It's about to die. That's why I brought my charger. So I saw it in time. So now, because this surface area gives you the material, right, needed to manufacture the can. So then the second step is, he said, write the surface area in terms of height and radius, right? The surface area is area of the top plus area of the bottom plus the side, area of the side, which is the curved surface, right? The curved surface. Let's say you have a page, a sheet, and you bend it to make it a cylinder, right? Now that sheet, the area of the sheet is exactly the area of the curved surface, right? And then you put a top, circular top and circular bottom, up and down. So the top has the area of top and bottom both are pi r square because they both are circles with radius r, right? Because the top has the radius r. So what is the area of this circle? Top and bottom, pi r square, right? So this is the top and the bottom are both the same. Cylinder has the same top and bottom, right? And then the curved side is, if you want to find this area of outside, so what you do, you take the outside boundary, that is the circumference of the circle, which is 2 pi r. So if you multiply this outside boundary by the height, it will give you only the outside boundary of the. So curved surface area is 2 pi r and multiplied by the height. So if you multiply 2 pi r into h, gives you the outer boundary. If you multiply the inside, let's say if you multiply this inside area pi r square, if you multiply this inside area by the height, it will give you everything which is inside. So pi r square into h gives you the volume inside, because you took the inside portion of the circle and multiplied by the height. So everything which is inside is included now. If you only take the outside boundary, right, outside boundary, and multiply by the height, it's like placing a circle on a circle on a circle. You know, you wear bangles, right? I don't know what you call them, bangles, right? They are circles, outer only. If you put one on top, you see, you got a cylindrical shape, and inside there is nothing. just outside boundary. So how you calculate? You can just count the bangles. If you put 100 bangles, right, it will give you the circumference of 1 multiplied by 100 multiplied by the height, gives you the outer area of the cylinder. Okay, so now this becomes my area. So surface area becomes 2 pi r square, because pi r square plus pi r square is 2 pi r square plus 2 pi r h. Now again I have two variables here. Two variables r and h. I cannot go ahead. I have to find something that changes to it from two variables to one variable. So look for a condition. It means some condition will be given. See, the first sentence is a condition. He said this cylindrical can has to hold 1 liter of liquid, 1000 centimeter cube, right? So what it given is, now the given condition is, given that the volume has to be 1000. Volume of the can has to be 1000 centimeter cube. 1 liter, right? What is the volume? Volume is pi r square h is equal to 1000. Right? This is given. Volume is given. We are not maximizing the volume now. We have to keep the volume fixed at 1 liter. So now from here my h will become 1000 divided by pi r square, right? So this is the condition that I got, and now I can replace it here. I can replace it here. So therefore my surface area becomes 2 pi r square plus 2 pi r h. So I can put h here now. H is 1000 by pi r square. So now I got one variable, right? One variable only. So this is good. So again we are happy, right? So with one variable I can work. I don't have anything with two variables. This is the issue. So now I can cancel. Pi will be cancelled. 1 r will be cancelled. So I got 2 pi r square plus 2 into 1000 becomes 2000 divided by r. So this is my. And now my radius has to be positive. That's the only thing I know. Right? Because volume is fixed, I cannot include r is equal to 0 here. You see, previously I included 0. I said if volume becomes 0, no problem, because they did not fix it. They said make the volume as large as possible. So we can start with 0 and make it as large. But now they are saying volume has to be 1 liter, 1000 centimeter cube. So I cannot take radius 0 now. So now radius has to be positive. Okay, and no limit. How long can be the radius? I don't know. It can be as much as possible. I don't know. Right? I can make height as small as possible to make the volume 1 liter. Keep the volume 1 liter. So that's why, see, it's an open interval and infinite interval. So basically I have infinite interval from 0 to infinity. Right? So see, infinite interval. It is called semi-infinite because it is half infinite. From the other side it is open. So see, it is open as well as infinite interval. So it's not a closed interval. So then we have an issue. In open and closed interval, it's not that easy. But we hope that we get only one critical point. If we have one critical point only, the relative maxima becomes absolute maxima. Relative minima becomes absolute minima. So that's an easy thing. So we hope that we get one critical point. But anyway, let me write the question first. Minimize. This was the question of minimize. They said find the least possible material. So least possible material means my surface area should be as small as possible. So minimize S over an infinite interval 0 to infinity. This is what I have to do now. Okay, so let's see how we can go from here. So first of all, finding critical point. Okay, so step 1 is always the same. Find critical points. S prime r is equal to 4 pi r and minus 2000 by r square. Derivative of 1 over r is minus 1 over r square. That's how I got this. So now I will set this equal to 0. Set s prime r equal to 0. That will give me 4 pi r equal to 2000 by r square. This will give me r cube is equal to 2000 by 4 pi. I can bring r square there and 4 pi down there. So we got this one, and now if I take the cube root, right? So this implies that my r is equal to cube root of 2 2s are 4 and 2 1000. Cube root of 1000 is 10 divided by 2 pi cube root power 1 by 3. This is what I got. So if you use calculator, I think 10 pi divided, yeah, see 10 over 2 pi cube root. It's correct, right? So 5.4, almost 5.4 inches. Okay, so this is my r. This is the only critical point. So if you have only one critical point, we are again happy. This is only critical point. Whenever your interval is infinite, but you have only one critical point, then it will either have this shape or this shape. Means this critical point where your derivative is 0, this shape, or your derivative is 0. So see, if it is relative minima, you see this shape is concavity upward. So second derivative is positive here. And second derivative is negative here. If you have only one critical point, your graph will never come back up. Then this point will become absolute maxima. You see? Absolute maxima. Why we are saying that it is absolute maxima? Because my graph will never come back up and go above that. Why it will never happen? Because if it turns, there will be another critical point. Whenever a function takes a turn, there is a critical point. And I know that there is no other critical point. If there is no other critical point, it will never turn back up. It will keep going down from both sides. Okay? It will keep going down from both sides because there is no other critical point. Got it? So that's why only checking the maximum is enough. See, this is the issue with the... I just saved it, I guess. Right? So let's see if I save it or not. Open. If I didn't save it, it's gone. Today at 9:16. So 3 minutes ago I saved it. So I have something, hopefully. Yes, I got it back. And how much I got it back? Yeah, most of the part is back, right? So I can write again, s prime r is 4 pi r minus 2000 by r square. So we set s prime r equal to 0, and this gives me 4 pi r equal to 2000 by r square. So this gives me r cube is equal to 2000 by 4 pi, and if you divide by 2, it is 1000 by 2 pi, and then if I take the cube root, it becomes 10 over cube root of 2 pi. So that is almost 5.4, right? That was the answer. So I got it. So this is the only critical point. This is the only critical point. So when you have only one critical point, we can just check the second derivative. Okay. So if it is an only critical point, just check the second derivative, s double prime. So what is s double prime r? 4 pi r becomes 4 pi, and minus 2000 by r square will become plus 4000 by r cube. Because derivative of r square is r minus 2. If I take the derivative, it becomes minus 2 r to the power minus 3, which is minus 2 by r cube. So that's why it becomes plus 4000 by r cube. Okay. So now you see it is positive. At So if I check S prime at R, which is 5.4, 10 over cube root of 2 pi, it will remain positive because there is nothing negative, you see. 4000 divided by whatever you have cube, but this is positive. R is positive, so everything is positive, you see. So I am only interested in whether it's positive or not. I don't need the value of second derivative. So second derivative positive gives you S is minimum. S is minimum at R is equal to 10 by cube root of 2 pi. Okay, so why this is minimum? Because second derivative is positive. We said that why we say that it is minimum when you have this type of shape. If your first derivative is 0 and the second derivative is positive, then you have this shape. And because this is the only critical point, it will not come back down. This is what I was explaining. If it comes back down, there are values less than that, so it means this is not a minimum, right? But we are sure that it will never come back down. Why it will never come back down? Because there is no other critical point. It will not turn. To turn it back down, I need another critical point which is not there. So it means it will keep going up, keep going up. Alright, so only critical point has this benefit that relative minima becomes the absolute minimum. Actually, this is the test for relative minima. This is the test for relative minima in section 4.2. Okay, but in 4.4 we studied that if we have only one critical point in infinite interval, not in closed interval, remember, in infinite or open interval, in both of these, then we have the same test for absolute minima. Then same test can be used for absolute maxima. Here in statement problems, we find absolute maxima. He said get the maximum, the highest value of the function, not the smaller. Relative maximas were like this. These are all relative maximas in their own vicinity, right? These are all relative maximas. These are all relative minimas. All relative minimas. We are not looking for that. We are looking for one maximum and one minimum value. One maximum is this one, the highest one. This is the absolute maximum. Okay, so we are looking for this in 4.4 and 4.5. So that's why I use the same test here, and I said the relative minimum, the absolute minimum of S is when R is 1 by 10 by 2 square root of 5. So my answer is, he said, hence the surface area is minimum, hence the surface area or material needed is minimum, when R is 10. He said what height and what radius should we choose, right? If this is R, then H was, remember, it was 1000 divided by 4 pi. What was H? H was 1000 divided by pi R square. So I can find H from here as well. 1000 divided by pi R square. So R is 10 by 2 pi cube root square. So if you simplify this, you will get the height, which is 20 by 2 pi. Double. See, double the radius. So next time, check out the 1 liter can when you go to Lulu or somewhere. Okay, you will see that maybe the radius is the height is double the radius. But if it is not double the radius, it means they did not worry about the minimum cost, right? They just wanted a predetermined size and they just made the cans. Otherwise, here it's almost height should be double. So if this is your radius, then double the height. Okay. So this type of can should be there to hold the 1 liter inside, and you see this is R and height is twice the R. It gives me exactly 1 liter of volume inside with the minimum surface area. Okay. So anyway, let's see. I can do one example from the exercise. These are all examples. Examples are solved usually easy, right? Find a number in a closed interval such that, see the first question, exercise set 4.5. I can give you hints for both maybe, right? And you can complete that. So this is on page 283. So let's see the first one. Okay, find the number. So I can say that let x be the number, right? Let x be the number, a required number, such that the sum of the number and its reciprocal, then the sum s, let's call it s as for the sum, right? Of x and its reciprocal. What is the reciprocal of x? 1 over x. Reciprocal is 1 over x, right? Is this. So they ask me this one, the sum of x and its reciprocal, x plus 1 over x, is as small as possible and as large as possible. It means I need to find both maximum and minimum, right? So it means I have to find maximum and minimum of s over the interval. What is the interval given? 1 by 2, 3 by 2. This is what I want. Okay, so this is my question now. Finding maxima minima of both. So let's see. Again, for maxima minima, I need the derivative of x. So x is 1 plus 1 over x is minus 1 over x squared. So this is what I got. Now set s prime x equal to 0. If I set it equal to 0, I got 1 equal to 1 over x square, x square equal to 1. So x is equal to plus and minus 1 both, right? But my only critical point is x is equal to 1. I will ignore the minus 1. Why? Because this is the only x in my given interval. 1 by 2, 3 by 2. So I will reject the negative 1. Reject x is equal to minus 1. Why? Because it is not in my interval, right? Because it is not in 1 by 2, 3 by 2. He said find the interval in this interval. Find the value in this interval only. So I got this critical point. Now because my interval is closed, you see, my question is finding maxima minima over a closed interval. So I have a different test for a closed interval. For a closed interval, we evaluate the values at endpoints and at the critical points. So my step 2 here is, after finding critical points, I will not go for the second derivative. I will evaluate s at critical point 1 and at endpoints 1 by 2, 3 by 2. Okay, so let's evaluate s at 1 by 2. So see, my interval was 1 by 2 to 3 by 2, and I got 1 in the middle here. So I have these 3 points to evaluate my s. So s was 1 by 2 plus its reciprocal. So that is 2. So 2 plus 1 by 2 is 2.5. 5 by 2. Then s at 1. 1 plus its reciprocal. So that is 2. And s at 3 by 2. So that is 3 by 2 plus 2 by 3. So 1 over 3 by 2 is 2 by 3. So if you calculate this one, what is that? 3 by 2 plus 2 by 3 is equal to 13 by 6. 13 by 6 is 2.17. 2.1666666, right? 2.167. So which is the largest? 2.5 is largest, and which is the smallest? 2. So my maxima and minima, right? So it means the sum is largest. So hence I can write the answer. He said as small as possible in A part. He said two things. In A part he said as small as possible and as large as possible, right? Yes, the first one is as small as possible. So I need small. So the sum is smallest. Sum is smallest when x is 1 and b the sum is large. He did not ask me the largest sum and smallest sum. He only asked me to find the number. He said find a number that gives you the smallest sum. So I got number x is equal to 1 by 2. So 1 by 2 will give you the largest sum of itself and its reciprocal, and 1 will give me the smallest sum. Okay, so that's one thing. For the second one, I can give you the hint here. Okay, what is the hint? He said, how should two non-negative numbers be chosen? So we can say that let x and y be two non-negative numbers, right? So that their sum is 1 and the sum of their squares is as large as possible. So one condition is given that x plus y has to be 1, right? So from here I can write y is equal to 1 minus x. And then he said the sum of their squares. So let's say s is the sum of their squares, x square plus y square, as large as possible, as small as possible. So it means I have to make this sum larger and smaller. But here we have two numbers, two variables, x and y, not one. That's why they gave you the condition, right? So this will become x square plus 1 minus x square. So now you will find the maximum and minimum of s over the infinite interval. It is not closed interval now. So my s, so I will maximize my s. So you can simplify. This is, I think, 2x square minus 2x plus 1. 1 minus 2x plus x square. So x square plus x square will become 2x square. So you have to find both maximum and minimum of this s over the interval 0 to infinity, because he said non-negative numbers from 0 to infinity. 0 is included, right? So non-negative means your x and y both are positive, greater than equal to 0. X is greater than equal to 0, y is greater than equal to 0. So 0 is included, but other side is infinity. So we can expect that I get only one critical point. And you can see that if I take the derivative, it will be 4x minus 2. Put it equal to 0, x will be 1 over 2. So only critical point. If you have one critical point in infinite interval, right, you can just check the second derivative. If second derivative is positive, it will give me minimum. If it is negative, gives me maximum. Okay. So smallest value will be 0. You know, if x and y both are 0, s is 0. Right? Okay. So I can stop here.